Hi, class. So I forgot to finish up that last lecture with section 12.7. So this is it. So we're going to talk about catalysts now. And let me go straight to my PowerPoint that I have planned for this. I'm going to do this on my desktop. I'll stop my video here and start this slideshow on catalysts. So catalysts speed up chemical reactions. That's what they are for. So we're going to go into how they do that. But one of the primary things is the catalysts are not consumed in a reaction. And so they're not included in the chemical reaction equation. The other thing about catalysts is it only takes a small amount. Since they're not consumed in a reaction, you don't need as much catalyst as you do reactant. So catalyst speeds up the reaction, but the more catalyst you have, the faster it's up. So that makes a difference. But the point of catalyst, it's not used up in the reaction, it's not consumed, and you don't need very much of it. So when you write a chemical equation that includes a catalyst, you just write catalyst over the reaction arrow. And usually instead of CAT, if it's a generic catalyst, you say you want to include a catalyst in the reaction, you just write CAT for catalyst. Otherwise, you'd write the formula for that catalyst. Catalysts are often homogeneous. Well, there's two kinds. They are homogeneous or heterogeneous. I've used catalysts a lot. Usually they're homogeneous, and a typical homogeneous catalyst is an acid. And probably in some of your reactions that you've done, you've used acid as a catalyst. In that case, if acid was a catalyst, you'd put an H+ over the reaction arrow to indicate that you're using an acid catalyst. So a homogeneous catalyst is a catalyst that exists in the same phase as the reactant. And so enzymes in our cells and our bodies, in biochemistry, enzymes are the biological catalysts. They exist in the same phase as the reactant molecules and the product molecules. Heterogeneous catalysts exist in a different phase, and metals are oftentimes used as heterogeneous catalysts. Palladium is a typical metal. Platinum is used. And these, because they're solids, they're used as solid catalysts in a liquid or gaseous phase reaction. Okay, so how do catalysts speed up the reaction? Well, in the last segment in the previous lecture, we talked about the activation energy. What catalysts do is they lower the activation energy. So if you look at the reaction profile of a typical reaction, it has a activation energy shown by the red line. If you add a catalyst to the reaction, the activation energy is going to be decreased. So in this case, you probably have the same transition state, but the transition state is in the catalyzed reaction has a lower activation energy. And that might be because of orientation of the molecules. I have a couple slides that are schematics of homogeneous and heterogeneous catalysts. So we'll look at those later. And they show kind of what one thing that catalysts do. Remember, there are three parts that we talked about collision theory. There's the concentration, the kinetic energy of the reactants, and also the orientation of the reactant molecules. So catalysts help in all those three aspects to lower the activation energy. This is another reaction profile. So again, the typical reaction on the red line and the catalyzed reaction on the lower line. This double peak indicates that the catalyst has taken a different pathway to form products. So the catalyst allows the reactant molecules to react by a different pathway that have a lower activation energy. And in this case, the catalyzed reaction has two activation energies. It has a intermediate. This is unstable intermediate here in the little valley between the activation energy peaks. The activation energy for the overall catalyzed reaction is the highest peak, showing on the left here. And it's significantly lower than the activation energy for the uncatalyzed reaction, so the reaction goes faster. It goes faster and at a lower temperature. So those are two big advantages to catalyzed reactions. In this third picture of a catalyzed reaction, here's one that has a very circuitous pathway, but the highest activation energy in the catalyzed reaction is still much lower than the activation energy of the uncatalyzed reaction. And this third reaction profile is typically what a biological or biochemical process looks like. So if we look at say sugar, you can take sugar and you can burn it and change it to CO2 and water. Well, that's what our body does too. It changes sugar into CO2 and water and extracts the energy from those. Well, the pathway for converting sugar to CO2 and water in our cells takes about 9 or 10, I don't know, 9 plus maybe 15 different reactions. So there's 15 little activation energies that are all less than the than if you had to if you actually burn sugar to change it into CO2 and water. So this might be what the pathway would look like for biochemical catalyzed reactions. So here's just a schematic showing the difference between homogeneous and heterogeneous catalysts. In the homogeneous case, the catalyst is here showing by this yellow dot, and it's in solution. And in this case, it looks like the catalyst is helping, it grabs both reactant molecules, holds them together so that a new bond can form, then it releases them. And then the catalyst is freed, it goes back to do that again. So you could put a little arrow back here and the catalyst is going to go back and help the two reactants, the green and the red reactant, meet up. So they really, so this is a case where the, in this schematic, the homogeneous catalyst is helping to orient the molecules in the right orientation so they can react quickly. And that's what enzymes do. So the biological catalysts in cells help orient the molecules. And that allows the chemical reaction to occur at much lower temperature under much more mild conditions. And biologically, that would be a rather neutral pH and maybe body temperature or room temperature, you know, so not extreme temperatures. In the second schematic here, it shows it's a schematic of a heterogeneous catalyst. So here's the catalyst surface. This could be a metal, like I said, palladium or platinum. And the two reactant molecules settle on this metal. And again, this metal holds the reactant molecules in close proximity so they can react. And then they get released. So that's how, so the catalysts are enabling the orientation, and they enable, because the molecules are oriented properly, the reactions can occur at a lower temperature. They don't need as much kinetic energy. And that's about it for catalysts. So let me get out of here, and we'll go back here, and I'll stop my screen share. Turn the video back on. And so that ends chapter 12. So if you have any questions, like I said in the last video, you can come to the office hours on Thursday, and I'll help you then. That should enable if you've watched all these lectures and you've done the worksheets, you should be able to do the homework, and the homework is due on this Sunday. So good luck with that. Let me know if you have any questions, and goodbye for now.